derivatives from. Could you remind me how you got the secant?
Well, what we're doing, you see, if you have a difference of squares and it's variable minus constant, that was what we were talking about here first. I used u here instead of x. If you let the u be the square root of the constant times secant, then when you have major replacement, you'll have your square, secant square minus your square here. You factor that, and then you say secant square minus 1 is tangent square.
Okay, thank you.
So it comes from the trick you use if you have this situation where it's variable square minus constant square. Yeah, you have your bag of tricks. You have your three basic forms back here, and you have to know or figure out which trick is appropriate to which form.
Okay.
So much of this type of mathematics is a bag of tricks. You'll find that's true in the differential equations class. If you take that, there's a it's much of this same kind of calculus, actually. That's why the Math 175 is a prerequisite to the 333 class. What you do in third semester is not near so much of this sort of trickery and doesn't relate so much to the differential equations. Anyway, look at this one where you have the sum of squares, and the reason that I wanted to talk about it, we've talked about sum of squares tricks and some of these others, but what's interesting here, this is not a proper fraction. A proper fraction, when you're talking algebra, the degree of your denominator polynomial is greater than the degree of your numerator. But you see, as polynomials, these are the same degree. So if you have an improper fraction, the first thing you do is long division. You divide it down. And so that's up here. So this is Math 25. And so we set up our division problem, and whatever is here is exactly what it needs to be. So if you take this times that, it will be identical to what's above it in the dividend. And so this is a 1 because 1x squared gives you this x squared, which is just like that. So when you subtract, the first column disappears. That's your game, isn't it? And whatever else might have been here will be in another column. For your answer up here, for your quotient, you'll take it times every term you have in your divisor. And so the 4 will go over here. So you have to think of it that there would be a 0 here for this to go underneath. You can just as well as not say you're dividing into x squared plus all the zeros you might want to write. And so finally, when you subtract, your remainder will be the minus 4. So that means that your original fraction becomes your quotient, the 1 dx, and then the minus, and then the 4 dx over this. So then the integral that is to be done that's of the type that goes with this section is the integral 4 dx over x squared plus 4. And you can factor out the 4, so you're just looking at this. Now, this is a form that you actually learned in Math 170. If you look at the table that they give you at the start of Chapter 8, which is kind of a summary of the Math 170 recipes, you'd find that the du over a squared plus u squared is 1 over a arctangent. So if you've wanted to just say, well, I've learned that, and go to the answer, I wouldn't argue with you. Otherwise, you can do the substitution. So, doing the substitution, which proves the recipe, you have your sum of squares type situation, so the x will be the square root of the constant times tangent, and then the dx is the derivative of the tangent, which is the secant square, and then 4 plus 2 tangent quantity square gives you 4 times 1 plus tangent square, which is 4 secant square. Which reminds me, we better do this.